The morning light filters through shallow water, scattering into a mosaic of gold and blue over the coral heads. The reef is already stirring. Schools of damselfish hover near their anemones, parrotfish grind coral into fine sand, and cleaner wrasses dart between the gills of patient clients. But on the edge of a rocky crevice, two far more deliberate hunters prepare for a different kind of choreography. A grouper, thick-bodied and heavy-jawed, glides over the substrate, its mottled flanks shifting shades to match the coral below. Just ahead, a moray eel slips from its hole like a ribbon of muscle and menace, its sinuous form tasting the water with flicks of its mouth. Their eyes meet, one vertebrate staring from behind blunt strength, the other from a long coil of muscle and teeth, and then, without words or instinctive aggression, they begin to hunt together. The grouper and the moray eel represent two entirely different strategies of predation. The grouper is a pursuit hunter, built for sudden acceleration. Its stocky frame conceals a powerful burst of thrust, allowing it to lunge at prey with astonishing speed. But this design comes with trade-offs. The grouper is clumsy in tight spaces, its wide body unsuited for the labyrinth of coral tunnels where smaller fish often flee. The moray, by contrast, is the perfect inverse. Its narrow, flexible body can thread through the smallest crevices, but it cannot chase prey in open water. When hunting alone, both species are formidable but limited, each a master of one domain, yet blind to the other. Together, they overcome those limits through one of the most remarkable examples of interspecies cooperation in the marine world. It begins with a signal. When a grouper spots a moray, it performs a distinctive head shake, rapid, deliberate, and unmistakable. Sometimes it tilts its body at a specific angle, hovering near the eel's den, a clear visual cue that carries through the flickering light of the reef. The moray responds with hesitation, reading not dominance but invitation. If it accepts, the eel emerges fully, its body unfurling into the open. Side by side, the two predators move out across the coral field, each aware of the other's role. The grouper leads, scanning for potential prey, small wrasses, squirrelfish or parrotfish that dart among the coral heads. The eel trails closely, weaving through crevices and holes, the shadow to the grouper's force. Field researchers studying this behavior have documented the precision of these interactions. In the Red Sea and the Indo-Pacific, groupers initiate cooperative hunts with moray eels in distinct sequences of gestures. The headshake functions as a recruitment signal, while a series of pointing motions, where the grouper hovers and dips near a coral head, indicate the location of hidden prey. These gestures are not instinctive displays like courtship or aggression. They are contextual and flexible, evidence of deliberate communication. Experiments show that when a grouper gives this signal, the moray responds correctly more than 80% of the time. When the signal is withheld, cooperation rarely occurs, and both predators' hunting success drops dramatically. The reef becomes a stage for calculated partnership where strategy trumps strength. The dynamic unfolds with subtle tension. A small wrasse darts for cover beneath a coral table, pursued by the grouper. It vanishes into the maze of branches where the grouper's bulk cannot follow. But before the prey can relax, the moray eel glides in from another angle, its serpentine form slipping effortlessly into the coral's underside. The wrasse bolts back into open water, directly into the grouper's waiting mouth. The capture takes less than a second. Both hunters benefit. The grouper claims the meal, but the next strike may favor the moray. Over the course of multiple hunts, the rewards even out. Cooperation persists because it pays. This partnership is one of the few documented examples of coordinated hunting between fish species, a level of collaboration once thought restricted to mammals and birds. Yet here, under the sea, two cold-blooded predators navigate a social contract that is both flexible and conditional. The grouper's signals are not orders but requests, and the eel's participation is voluntary. If the grouper betrays the partnership by taking all the prey or by failing to lead efficiently, the moray will refuse future invitations. In controlled studies, researchers observed that eels ignore groupers who fail to reciprocate. a behavior consistent with what biologists term reciprocal altruism. In essence, the eel keeps score. The reef, for all its apparent chaos, hides an economy of trust. Evolution has fine-tuned both partners for their roles in this silent negotiation. The grouper's eyes, positioned forward rather than to the side, grant it binocular vision, a rarity among fish and a crucial advantage for depth perception during hunting. Its large pectoral fins allow it to hover precisely, making its gestures readable to other species. The moray, meanwhile, possesses one of the most complex feeding mechanisms in the animal kingdom. Beyond its outer jaws lies a second set of pharyngeal jaws, modified throat bones lined with teeth that can shoot forward to grasp prey and pull it inward. This dual-jawed system allows the eel to feed within tight spaces where suction feeding would be impossible. Together, these anatomical specializations create a perfect synergy of muscle, stealth, and communication. The ecological implications of this alliance reach beyond the individual hunt. Cooperative foraging enhances predation efficiency, shaping prey behavior and reef community structure. Fish that might otherwise rely on coral labyrinths for refuge must now adapt to predators that can breach both open and hidden domains. In areas where grouper-moray cooperation is common, prey species exhibit heightened vigilance and altered foraging patterns, spending less time in exposed zones. Over generations, this pressure may even influence morphology, favoring slimmer, faster fish capable of evading both pursuit and ambush. In this way, two predators working together can alter the evolutionary trajectory of an entire ecosystem. From a behavioral perspective, this alliance challenges long-held assumptions about fish intelligence. The coordination between grouper and moray suggests not only communication, but cognitive planning. Groupers have been observed approaching morays specifically when prey has escaped into crevices, implying an understanding of the eel's abilities. In experimental setups, groupers even recruit morays to artificial structures where prey are hidden, displaying problem-solving behaviors that parallel cooperative hunting in higher vertebrates like dolphins or wolves. The reef, it seems, is home to minds far sharper than we once imagined. Underwater cameras capturing these hunts in slow motion reveal the precision of timing that underpins success. When the grouper points toward a coral head with a downward tilt of its body, the moray moves in almost immediately, probing with its head until the prey bolts. The grouper, already positioned at the exit, lunges within fractions of a second. When researchers remove either partner from this sequence, hunting efficiency plummets. The data confirm what observation already suggests. The partnership is not incidental but strategic, maintained because natural selection rewards cooperation that increases total yield. The balance of power, however, is delicate. Not all groupers are equally adept at communication, and not all morays are willing collaborators. Younger or inexperienced individuals often misinterpret signals or act out of sync, leading to failed hunts. In these cases, the partnership dissolves quickly. Over time, both species learn which individuals to trust. This selective collaboration hints at a form of partner choice, an ability to evaluate reliability and adjust behavior accordingly. Among fish, such selective cooperation is rare, bordering on the cognitive sophistication typically associated with social mammals. Even more intriguing is how these interactions vary across environments. In the Red Sea, where coral complexity provides abundant hiding places, grouper-moray cooperation is frequent and well-developed. In the Caribbean, where coral cover is declining, the behavior is rarer, perhaps because structural simplification reduces the need for such specialized teamwork. This correlation underscores a broader truth: complex ecosystems foster complex behavior. The reef's diversity creates both problems and opportunities, and intelligence evolves as a tool to navigate that complexity. As dusk settles and the reef's colors dim, the two hunters part ways. The grouper drifts toward deeper water, its body blending into the shadowed blue, while the moray retreats into its crevice, folding itself into a coil. The day's partnership dissolves without ceremony, yet tomorrow it may begin again with a single tilt of the head. In the quiet that follows, the reef returns to equilibrium, the prey once again daring to move among the corals. What endures beyond the moment is the insight. Cooperation is not the exclusive domain of mammals or birds. It arises wherever survival demands flexibility, where instinct alone is not enough. The grouper and the moray eel, each born to different worlds of movement and form, have evolved a language of gestures that turns competition into alliance. In a realm where most interactions are driven by predation and defense, their partnership stands as a reminder that even in nature's most ruthless systems, intelligence often manifests as the ability to share. And in the silent depths of the reef, that shared understanding is written not in sound or words, but in the subtle tilt of a predator's head and the silent glide of another answering the call. The reef at dawn is a city waking under filtered light, its towers of coral casting blue shadows, its streets patrolled by fish in shifting prismatic traffic. Currents slide over the surface like wind through canyons, carrying the sense of mucus, salt, and decay. In this crowded world of color and motion, one shape is almost invisible until it moves. A head, slick and scaled, peers from a hole in the coral. A mouth opens and closes rhythmically, exposing rows of fine teeth. The body behind it is hidden, a ribbon of muscle coiled deep into the limestone. This is a moray eel, one of the reef's most patient engineers of death. Yet the story that matters here is not just its anatomy, nor the infamous second set of jaws that have made it a staple of ocean legends. It is the pact this eel keeps with another predator, the grouper, and the strange trust that allows two killers to hunt as one. The moray's partnership with the grouper is an alliance that defies our usual image of marine predation. Fish are not supposed to cooperate across species lines. Their world, shaped by competition and scarcity, seems too brutal for partnership. Yet on certain reefs in the Indo-Pacific, these two predators have formed a recurring and measurable agreement, one that depends on both memory and place. Groupers recruit morays for help when prey flee into the coral maze. The eel, capable of navigating narrow crevices, dives in to flush the victim into the open, where the grouper waits. Both parties share in the spoils, though not always evenly. What keeps the cooperation going is that, on average, both win more often together than apart. The first clue to the depth of this relationship lies not in the hunt itself, but in its geography. Repeated field studies have shown that these interactions are not random encounters between strangers. They occur at specific points on the reef, stable zones of overlap between the moray's fixed home range and the grouper's patrol route. Researchers call these areas meeting corners. They are usually found where coral channels intersect or where limestone ridges funnel fish movement, junctions in the reef's architecture that magnify chance into pattern. Here, morays and groupers seem to recognize one another as reliable partners. When one arrives, the other often follows within minutes, as though responding to an unspoken appointment. To understand how this works, one must first know what it means to be a moray. Unlike most reef fish, the moray eel does not roam widely. Its world is a network of tunnels and chambers carved into coral or rock, spaces it knows intimately through touch and chemical scent. Its body, lacking scales, is coated in mucus that protects it from abrasion and parasites, allowing it to glide through passages no other fish can enter. Its eyes are small and poorly suited for color vision, but its nostrils, elongated, flared tubes on its snout, grant it an extraordinary sense of smell. For the moray, water is information. Every molecule that passes over its nostrils tells it who has been here, what has bled, and where the currents have carried the trail. When a grouper signals, it is the chemical trace as much as the sight that draws the eel out. The invitation begins with a gesture. The grouper hovers near the moray's hole, body tilted slightly downward, pectoral fins quivering. Then comes the head shake, sharp, lateral movements repeated several times. The meaning is clear in context. Prey is nearby, hidden in coral, inaccessible to both unless they work together. The moray responds by easing forward, tongue flicking from its mouth as it samples the scent. If the invitation is accepted, the eel slips free of its den, its body undulating in precise S-curves. Side by side, predator and ally begin their patrol. The grouper's large fins stir sand and detritus. The moray slides beneath coral shelves, its head emerging intermittently like a periscope. The cooperation is not choreographed, but adaptive. When a prey fish bolts into a hole, the grouper stops short, hovering above the entrance. The moray plunges in, its long body twisting through the coral labyrinth. Within seconds, panic erupts inside the crevice. A flash of scales, the faint clicking of jaws, and then an explosion of movement as the prey bursts from the opposite exit. The grouper, already in position, lunges. The strike is over before the moray even reappears. Both partners remain still for a moment, as though resetting their balance. Sometimes the grouper eats. Other times the moray emerges with a struggling morsel clasped between its jaws. There is no sign of conflict, no attempt to steal. The unspoken contract remains intact. This level of cooperation implies a kind of spatial memory. Observations show that certain morays and groupers reunite repeatedly at the same reef junctions, sometimes weeks apart. The partnership appears to be built on individual recognition, a rare behavior in fish, but not impossible. Both species possess large optic lobes and a basal ganglia system capable of forming associative memories. The grouper remembers which moray emerges reliably, and the eel remembers which grouper does not cheat. In experimental setups, when unfamiliar individuals are introduced, cooperation drops sharply. Success depends on familiarity, not just proximity. This suggests that what we are witnessing is not instinctive behavior, but learned collaboration. The moray's role is especially intriguing because it combines predation with exploration. Within the coral, the eel's movements generate microcurrents that disturb silt and small invertebrates, effectively probing the structure like sonar. Its lateral line system, sensitive pores along its body that detect pressure changes, maps the contours of the labyrinth in real time. This allows it to maneuver through complex three-dimensional spaces with astonishing speed. When it flushes prey toward the grouper, it is not random luck but spatial calculation. The eel anticipates the path of least resistance, the direction the prey is most likely to flee, and aligns its attack accordingly. Meanwhile, the grouper provides muscle and reach. Its strike velocity can exceed body length per second, creating a shockwave of displaced water that stuns prey even if the jaws do not make contact. Yet, it is the moray's entrance that triggers the kill. The combination of stealth and shock compresses the prey's options to zero. When viewed from above, the pair behaves almost like a single organism. Two bodies, one strategy. But what ensures the moray's continued cooperation? Evolutionarily, cheating would seem tempting. After all, the moray could ignore the grouper's invitations and focus solely on its own hunts. The answer lies in efficiency. Prey availability on coral reefs fluctuates with time, tide, and season. By cooperating, both predators expand their effective hunting territory and increase the diversity of prey they can capture. The moray gains access to more opportunities without leaving its familiar range. The grouper gains entry to the reef's hidden infrastructure. Over evolutionary timescales, selection would favor individuals who recognize and exploit such partnerships. The behavior becomes not just opportunistic, but culturally reinforced within populations. Recent experiments in the Red Sea used remote cameras and acoustic tagging to map these encounters over months. The data revealed that cooperative hunts cluster along reef highways, corridors of current and structure that channel both prey and predator traffic. These intersections serve as ecological marketplaces where individuals from different species converge repeatedly. The concept of a meeting corner is not metaphorical, it is measurable. Morays returning to the same coral cluster were recorded up to 10 times more often than random expectation. The reef, in other words, contains predictable venues for interspecies collaboration, fixed locations where intelligence meets geography. Even the act of signaling reflects sensory constraints. The grouper's headshake is visible across a few meters, but not much farther. It must occur within the moray's visual and olfactory field. That limitation may explain why such cooperation has evolved here and not elsewhere. It requires the intimacy of a dense, structured habitat where sightlines are short, but neighbors are familiar. In open ocean systems where visibility and distance separate hunters, such signals would be lost to the current. The coral reef, with its complex geometry, provides the perfect stage for gestures that mean something. Underwater footage captured during controlled observations adds another layer of insight. When a grouper initiates a hunt, but the moray fails to emerge, the grouper waits, often for minutes, hovering near the crevice and repeating its head shakes. If no response comes, the grouper eventually departs. However, when the same grouper later approaches a different moray, it adjusts its signaling frequency, shaking more rapidly, as if compensating for the lack of established trust. These subtle modulations suggest behavioral flexibility, perhaps even negotiation. The grouper's persistence mirrors that of animals with complex social structures, where communication is iterative rather than instinctive. The moray's return to its den after the hunt completes the ritual. It slides back into the hole, reversing its path with uncanny precision. Inside, it rests among the bones and shells of past kills, the airless quiet broken only by the rhythm of its breathing. In this narrow world, the moray's senses remain alert. It remembers the shape of the grouper's body, the pattern of its signals, the spot on the reef where cooperation brought food. In time, when the vibration of fins passes overhead again, the eel will recognize the same partner and emerge once more to hunt. At first glance, this alliance may seem like an odd footnote in marine behavior, a curiosity among countless adaptations. But its significance runs deeper. The grouper-moray pact blurs the line between instinct and intellect, showing that even creatures separated by millions of years of evolution can converge on cooperation when ecological logic demands it. It reveals that intelligence is not a privilege of warm-blooded animals. It is a property of complexity itself, a natural response wherever two minds, however alien, find mutual advantage in understanding. By night, when the reef darkens and the plankton rise, the same corners that hosted the day's partnerships fall silent. Yet under infrared light, movement continues. A grouper glides past the moray's entrance, the faint shimmer of its scales just visible before it fades into the dark. A few seconds later, the eel stirs, lifts its head, and begins to follow. No words, no promises, no memory in the human sense, only the enduring rhythm of cooperation, repeated through generations. The meeting corner will still be there when dawn returns, and the reef's economy of trust will begin again, one signal at a time. Sunlight pierces the clear lagoon like glass needles, splintering across the coral heads and painting rippled mosaics on the seafloor. Amid the soft undulations of the reef, a sea anemone sways like a living crown, its tentacles translucent and trembling, tipped with quiet danger. To most fish, this is a death trap. A single brush against those stinging threads can paralyze or kill within seconds. But nestled among them, darting in and out with practiced ease, lives a creature immune to this toxic embrace. The clownfish, bright orange, white-banded and defiant against the pastel calm of its host, moves with confidence where others would perish. It is not merely hiding here. It is home, servant and tenant all at once. The reef's most improbable partnership plays out in these small, pulsating territories, a predator that shelters prey, and prey that protects its predator. At first glance, it appears that the clownfish is the clear beneficiary in this alliance. The anemone's venomous tentacles ward off nearly all would-be hunters, giving the fish a fortress from which to live, breed, and feed. Yet the relationship runs both ways, and the clownfish is no idle resident. Every flick of its fins, every patrol through the tentacles, performs labor that benefits the host. As the fish weaves between the columns, it fans fresh, oxygenated water through the anemone's body, improving circulation and waste removal. Its constant motion clears away sediment that might otherwise clog the anemone's tissues. The fish also defends its host from intruders, butterfly fish that bite at tentacles, crabs that scavenge too close, and other clownfish that attempt to usurp the home. In this sense, it acts as both gardener and guard, paying rent in vigilance and service. The protection the anemone offers in return comes not from leniency, but from chemistry. Its tentacles are loaded with nematocysts, microscopic capsules that fire venomous barbs on contact. These stinging cells are triggered by touch and chemical cues, exploding with pressures greater than a bullet's acceleration. How then does the clownfish survive among them? The answer lies in a remarkable evolutionary adaptation, a mucus shield that acts like a biochemical password. Unlike other fish, which carry skin coatings rich in proteins that excite nematocyst discharge, the clownfish's mucus lacks those triggering molecules. Over time, through repeated contact with its host, the fish also acquires chemical signatures from the anemone's own secretions, effectively cloaking itself in the scent of its landlord. To the anemone's tentacles, the clownfish becomes chemically invisible. It is not tolerated by the host, it is mistaken for part of it. The process of gaining this immunity is delicate. When a juvenile clownfish first approaches an anemone, it does not dive straight in. It hovers nearby, brushing tentacles in quick, cautious touches, retreating after each attempt. With every pass, a thin layer of mucus from the anemone transfers onto the fish. Over the course of several hours or even days, the juvenile gradually builds a protective mask of borrowed chemistry. Only when fully cloaked does it settle among the tentacles without harm. For the fish, this initiation is a gamble between life and death. One premature plunge, and the stings can overwhelm its defenses. Yet those that succeed inherit a living citadel, a space of both refuge and responsibility. The partnership extends far beyond mutual shelter. Within the boundaries of an anemone's reach, the clownfish maintains a strict social order. At the top of the hierarchy is a dominant female, the largest individual in the group, followed by her breeding male, and beneath them, a set of smaller, non-reproductive subordinates, all are born male. If the dominant female dies, the breeding male undergoes a hormonal transformation, changing sex to take her place, while the next largest subordinate matures to become the new mate. This succession ensures continuity but also enforces stability. Each fish knows its role, and physical size determines social rank. Any attempt to grow beyond one's station risks attack from superiors, a biological ceiling enforced by aggression and restraint. The result is a micro-society as disciplined as any primate troop or termite colony, ruled not by cooperation alone, but by constant negotiation of dominance. Yet this system, for all its precision, depends entirely on the anemone. Remove the host, and the hierarchy collapses. The family loses its shelter, its breeding ground, and its food base. The clownfish feed on plankton and small crustaceans, but they also rely heavily on scraps that fall from the anemone's meals and on the parasites that infest its tentacles. Without their host, the fish are forced into open water, where predation risk multiplies. For displaced families, relocation is perilous. Sea anemones are scattered unevenly across the reef, and suitable new hosts may lie hundreds of body lengths away. An impossible journey across exposed terrain. In one documented case, researchers tracked a clownfish family forced from its anemone after a passing storm overturned the coral base. For days, the group lingered near the wreckage, unwilling to stray far from the familiar tentacles. As algae began to overgrow the dead anemone, the dominant female finally led the migration. The small band set out across bare sand, a glowing procession of orange and white against the blue void. Predators quickly took notice. Wrasses and damselfish darted in pursuit, while a lurking lizardfish made lunges from beneath the sediment. By the time the group reached a new host, only 3 survivors remained. Such journeys highlight the fragility of their existence. Social creatures bound to a single organism, their fate tied to another's survival. Once settled again, the rebuilding begins. The female reasserts dominance, often punishing subordinates that fail to maintain order. The mucus exchange must start anew as the chemical identity of each anemone differs. The process of acclimation, that ritual of careful touches, repeats, reminding us that even within the illusion of stability, every clownfish is always one mistake away from being burned by its protector. Beneath this partnership lies a deeper evolutionary story. The mutualism between anemones and clownfish likely evolved millions of years ago, born from opportunism and refined by necessity. Early ancestors of clownfish may have been facultative associates, species that occasionally ventured near anemones to feed on leftovers. A few individuals, perhaps through random variation in skin chemistry, survived the tentacle's sting long enough to gain a foothold. Those survivors enjoyed a massive advantage: protection from predators. Natural selection favored those with thicker mucus or fewer nematocyst-triggering proteins. Over generations, the relationship intensified until both species became dependent on the other. Today, neither can be fully understood without its partner. From an ecological perspective, these alliances shape the structure of the reef itself. Anemones harboring clownfish grow larger and healthier than those without tenants. The constant fanning of water by the fish increases oxygen supply, while the removal of debris reduces infection risk. Clownfish waste, rich in nitrogen, acts as fertilizer, stimulating algal growth that benefits the anemone's symbiotic zooxanthellae, the microscopic algae that power its metabolism through photosynthesis. In return, the anemone's protection allows the fish to invest energy into reproduction rather than defense. It is a perfect economic loop, where the currency is nutrients and vigilance, and the profit is survival. But the equilibrium is fragile. Rising sea temperatures and coral bleaching threaten both partners. As coral structures die, many anemones lose anchorage and wither. Clownfish that once occupied stable homes are cast adrift, forced into overcrowded or unsuitable hosts. Studies have shown declines in breeding rates and increased aggression under such conditions, suggesting that environmental stress fractures not only the physical habitat but also the social fabric of these fish. When the landlord dies, the tenants lose more than shelter. They lose the foundation of their identity. Still, within the chaos, resilience endures. Even damaged anemones can recover if currents and nutrients allow. When they do, displaced clownfish often return, guided by chemical cues that lead them back to familiar sites. Their sense of home is acute. They recognize the precise signature of their anemone's mucus, the taste of their territory imprinted in memory. Such fidelity underscores how deeply the two species are entwined, not just spatially, but biochemically, behaviorally, and evolutionarily. As evening descends, the reef cools and the light fades to indigo. The clownfish retreat deeper into the anemone's folds, their bright bodies now pale under the twilight glow. The anemone's tentacles draw inward slightly, its cells conserving energy for the night. Together, fish and host become one indistinct shape, a single organism pulsing gently in the current. Around them, the reef breathes. Predators stirring, plankton rising, the cycle of risk and refuge continuing as it has for millennia. What appears from above as a small splash of color hides one of the ocean's most intricate contracts. Here, life is negotiated molecule by molecule, gesture by gesture. The clownfish's every move, its cleaning, its guarding, its cautious dance among venomous arms, is both tribute and transaction. In a world where survival is measured by millimeters and moments, it pays its rent not in coin, but in devotion, maintaining the fragile balance that turns danger into home. At first light, the reef seems almost motionless, its inhabitants still waking beneath the soft sweep of incoming tides. Then, as the sun rises and the water warms, movement begins, a slow pulse of life spreading across the coral landscape. Amid this awakening, a sea anemone unfurls its tentacles like a living crown of translucent fingers, each one wavering gently in the current. The scene appears peaceful, almost ornamental, but this creature is no passive decoration. Hidden within its soft tissue is an intricate system of nerves, muscles, and chemical sensors tuned to the subtlest changes in the water. This is an animal that hunts, defends, and negotiates, an organism whose survival depends not on drifting idly with the sea, but on its ability to interact with its environment in astonishingly complex ways. And among the anemone's most remarkable relationships is the one it maintains with its tenants, the clownfish, those bright orange residents whose daily activity transforms the host from static predator into thriving ecosystem. Each tentacle of the anemone carries thousands of microscopic capsules known as nematocysts, tiny pressurized weapons that fire venomous harpoons at anything they touch. When triggered by the right chemical cue, usually the proteins found in fish mucus, these harpoons pierce cell membranes, injecting toxins that paralyze prey. Yet despite this arsenal, the anemone itself is remarkably vulnerable. Without mobility, it must rely on the environment to deliver both food and oxygen. Water movement across its surface determines its respiration rate, while sediment buildup and algal overgrowth can suffocate it. Here is where the clownfish enters the equation, not as a simple guest, but as an active caretaker. Every flick of the fish's fins helps circulate fresh, oxygen-rich water over the anemone's tissues. Every defensive charge against an intruder preserves the host's delicate structure. The clownfish, in effect, becomes the anemone's external organ, a living pump, fan, and sentry rolled into one. The relationship between the two species extends far beyond convenience. In controlled studies, scientists have measured growth rates of anemones with and without resident clownfish. The difference is dramatic. Those inhabited by fish can grow up to twice as fast, reproduce more frequently, and recover from physical damage at a far greater rate. The reason lies in the constant mechanical stimulation caused by the clownfish's movements. As the fish darts among the tentacles, it generates microcurrents that not only deliver oxygen, but also stimulate the anemone's nerve net, promoting tissue expansion and polyp division. In a sense, the anemone grows in response to touch. What looks like casual swimming is, at the cellular level, a daily workout regime that strengthens the host. The benefits are not purely physical. Chemical exchange forms an invisible dialogue between host and tenant. Clownfish excrete waste rich in nitrogen compounds, primarily ammonia, which the anemone's symbiotic algae absorb and convert into nutrients through photosynthesis. These microscopic algae, known as zooxanthellae, live within the anemone's tissues and supply it with sugars in return for protection and sunlight exposure. The clownfish's waste, therefore, fuels the algae that in turn feed the anemone. What emerges is a three-way economy of survival. The algae photosynthesize, the anemone provides shelter, and the fish power the system with waste and movement. In ecology, this kind of feedback is known as a mutualistic triad, where benefits cascade through multiple trophic layers. It is a living engine of reciprocity, tuned by evolution over millions of years. But the partnership has a behavioral dimension just as intricate as its chemistry. Anemones are not immobile in the way corals are. They can flex, bend, and even glide slowly along the substrate when disturbed. Using subtle contractions of their pedal disc, the fleshy base that anchors them, they can inch toward or away from light, current, or neighbors. When researchers filmed anemones over days and weeks, they discovered a surprising pattern. Anemones hosting clownfish tend to orient their tentacle crowns in the direction of regular fish traffic. The polyps literally flex toward the movement, maximizing contact with the currents stirred up by the clownfish. This feedback loop, fish stimulating water flow, anemone adjusting position to capture it, turns the pair into a responsive system, constantly fine-tuned by behavior. The anemone is, in a sense, watching its fish. Protection is the most visible aspect of this alliance, and nowhere is it more dramatic than when butterfly fish enter the scene. These brightly patterned grazers are among the anemone's most persistent enemies, specialized in biting off tentacle tips to feed on the nutrient-rich cells within. For an unguarded anemone, a single butterfly fish attack can strip away much of its feeding surface, leaving it weakened for weeks. Yet with a clownfish in residence, the outcome is very different. As soon as a butterfly fish approaches, the clownfish charges, fins flared, jaws snapping, body vibrating with agitation. The anemone, sensing the chemical disturbance and mechanical movement, contracts its tentacles in defense, drawing them inward like a closing fist. Together, fish and host repel the invader. The anemone's recovery rate and feeding efficiency are directly linked to how aggressively its tenants defend it. In the evolutionary bargain between these species, loyalty is a form of survival. The anemone's reproduction is also influenced by this partnership. Like many sea cnidarians, anemones reproduce both sexually and asexually. When conditions are favorable, they can split in two through fission or release small clones that grow nearby. These processes accelerate dramatically when clownfish are present, suggesting that the increased nutrient flux and water movement stimulate reproductive signaling. In this way, the clownfish does more than maintain its home, it propagates it. Over generations, this can transform sections of the reef into clusters of genetically identical anemones, each harboring its own fish colony. The reef becomes a patchwork of micro-empires, each built on the same biological contract of venom and vigilance. Perhaps the most intriguing element of this relationship lies in how anemones recognize and accept their tenants. When a new clownfish approaches, it must undergo a ritual of cautious introduction, touching the tentacles briefly before retreating, again and again. To the casual observer, this looks like nervous behavior. In reality, it is a biochemical negotiation. With every contact, the fish transfers small amounts of its own mucus to the anemone, while sampling the anemone's secretions in return. Gradually, the anemone's nematocysts become less reactive to the fish's chemical signature. Studies indicate that specific compounds in the clownfish's mucus, glycoproteins and lipids, trigger changes in the anemone's stinging cells, effectively disabling their firing mechanism for that particular scent. Once this handshake of chemistry is complete, the fish is accepted. This process can take hours or even days, but once established, the tolerance persists. If the fish leaves and returns weeks later, the anemone still remembers its chemical identity. From an evolutionary perspective, this capacity for recognition represents a kind of learning at the cellular level. The anemone's nerve net lacks a central brain, yet it exhibits a form of adaptive behavior. Its stinging cells can be selectively inhibited, and its tissue can remodel in response to consistent mechanical and chemical cues. In essence, it performs pattern recognition, an ability fundamental to intelligence, using only the distributed coordination of cells. In the microscopic world of coral reefs, where everything depends on timing and proximity, such decentralized intelligence can mean the difference between symbiosis and stinging death. Even without its fish partners, the anemone remains a predator of quiet efficiency. Small crustaceans and planktonic animals that brush its tentacles are immobilized instantly, reeled inward by coordinated waves of contraction. Yet the very presence of clownfish alters the prey dynamics around the anemone. The fish's movements attract plankton and small detritus, which become secondary meals for the host. At night, as the clownfish rest within the tentacles, their respiration continues to stir water and nutrients through the anemone's folds. The partnership never sleeps, it merely slows, synchronizing to the rhythm of the tide. In recent years, researchers studying ocean acidification and warming have noticed that this ancient partnership faces new pressures. Elevated carbon dioxide levels reduce the availability of carbonate ions necessary for reef stability, while rising temperatures threaten the zooxanthellae living inside the anemone's tissues. When these algae are expelled, a process known as bleaching, the anemone loses much of its color and nutritional support. Clownfish that remain loyal to bleached anemones can extend their host's survival by fanning water and defending it from scavengers, buying time for recolonization. In some cases, the presence of fish delays bleaching altogether by improving circulation and shading sensitive tissue. The same behavior that once evolved for mutual gain now serves as a last defense against climate stress. By nightfall, the reef darkens into shades of violet and gray. The current slows, and bioluminescent plankton shimmer faintly in the water column. The anemone's tentacles contract, its feeding slowed, while the clownfish retreat deep inside, pressed against the host's central column. Together they ride out the night, an unlikely duo whose destinies are entwined at every scale, from chemistry to behavior. The next morning, as light returns and the clownfish resume their steady fanning, the anemone flexes subtly, orienting its polyps toward the motion. What began in prehistory as coincidence has become a living conversation between species, one built not on dominance but on feedback. The anemone's survival depends on performance, and the clownfish's survival depends on acceptance. Their partnership is a living contract, written not in words or instinct, but in the flow of water, the exchange of chemicals, and the quiet rhythm of coexistence. Through them, we glimpse how even the simplest life forms, creatures without bones or brains, can engineer one of nature's most enduring alliances, transforming venom into sanctuary and danger into home. At low tide, when the reef lies half exposed beneath a thin film of retreating water, a tiny figure scuttles across the sand. Barely larger than a coin, The boxer crab pauses mid-step, its legs half raised, its claws extended like a fighter frozen in stance. In each claw it grips not a shell fragment or stone, but a pair of living sea anemones, miniature translucent organisms whose tentacles ripple and flare with every movement of their carrier. To the untrained eye, it might look like decoration, an odd quirk of reef life. But in truth, this pairing is one of the ocean's most remarkable exchanges, an alliance where weapons are borrowed, technology is alive, and the boundary between organism and tool begins to blur. The boxer crab, or Libia tessellata, is a small crustacean belonging to a genus that has perfected the art of biological appropriation. It cannot defend itself with brute strength. Its claws are delicate, its carapace thin, and its size makes it easy prey for fish, octopus, and even larger crabs. Evolution's solution was not armor or aggression, but partnership. In the absence of physical might, the boxer crab carries venom in its hands. Outsourced to anemones, it recruits and maintains as living weapons. These tiny cnidarians are far smaller than their free-living relatives. Their bodies are reduced to compact discs crowned with a fringe of tentacles, optimized for life as a crab's accessory. The crab, in return, provides mobility and access to food, carrying the anemones across the reef to fresh foraging grounds. It is mutualism weaponized, symbiosis turned into strategy. When viewed up close, the partnership's choreography reveals a precision that borders on design. As the crab moves, the anemones pulse gently, their tentacles brushing the substrate. Each step kicks up a thin cloud of organic detritus, bits of decaying algae, plankton, and microscopic life, which the anemones capture and ingest. In turn, the crab feeds on leftover fragments or mucus released by its symbionts, scraping food from the very partners it protects. It is an economy of proximity. No waste, no separation, every act of movement feeding both participants. At rest, the crab holds its anemones aloft, waving them slowly in front of its face as though testing the current. This posture, while defensive, also serves a respiratory function. The motion of the tentacles stirs water around the crab's gill chambers, improving oxygen exchange. The alliance sustains not only survival, but metabolism itself. Yet this partnership is far from static. The boxer crab's possession of its anemones is not a simple find-and-keep arrangement. It is an active relationship maintained through theft, negotiation, and cloning. Anemones are scarce on many reefs, particularly the small mobile species favored by these crabs. When two boxer crabs meet, their encounters often turn into complex displays, ritualized contests that decide ownership without bloodshed. The crabs stand on their hind legs, raising their anemones high like miniature banners. They wave them rhythmically, feinting and retreating in a dance that mirrors boxing but rarely ends in contact. The goal is intimidation through motion. The brandished anemones, shimmering and pulsing, send both visual and chemical signals of potency. When one crab finally yields, it retreats, and the victor continues undamaged. The duel is resolved not through violence but through performance. The anemones, however, are the true prize, and sometimes the casualties. If a crab loses one or both of its symbionts, it will go to astonishing lengths to replace them. Field and laboratory observations reveal a remarkable behavior: cloning. When deprived of one anemone, a boxer crab will gently tear its remaining partner in half, holding each fragment carefully until they heal and regenerate into two complete individuals. Both halves survive, each rebuilding the missing portions of its body over the course of several days. The process is a form of induced fission, a natural capacity in anemones that the crab has turned into a deliberate act of resource duplication. By splitting its symbionts, the crab effectively manufactures its own weapons, self-sustaining and endlessly replaceable. It is the biological equivalent of recharging ammunition. This cloning behavior raises profound questions about the nature of control and co-evolution. The anemones clearly benefit from being carried. They gain transport, access to food, and protection from predation. Yet they are also manipulated, divided, and used in ways that serve the crab's interests first. The relationship exists in a liminal space between cooperation and exploitation, a recurring theme in marine symbioses. Much like hermit crabs that use living sea sponges as shell covers or gobies that guard shrimp burrows, the boxer crab demonstrates how evolution blurs moral categories. In the ocean, partnerships are rarely altruistic. They are negotiations between opportunists. Ecologically, the boxer crab's behavior plays a subtle but significant role in the reef community. By transporting its anemones from place to place, the crab inadvertently disperses them across new territories, increasing their genetic reach. Each anemone clone the crab creates can eventually become an independent colony if separated. In this sense, the boxer crab is both gardener and vector, maintaining a mobile population of cnidarians that would otherwise remain confined to static substrates. It spreads life while wielding it as weaponry, a paradox that only nature's evolutionary logic could sustain. The mechanics of this alliance extend down to molecular communication. Both crab and anemone are covered in layers of chemical cues, proteins, lipids, and glycoproteins that identify friend from foe. When a boxer crab first acquires a new anemone, the pairing is preceded by a grooming ritual. The crab brushes its claws across the anemone's body, coating it with a mixture of mucus and secretions from its own cuticle. This process appears to pacify the anemone's stinging cells, preventing it from discharging nematocysts into its host. Over time, the two organisms develop a shared chemical profile, allowing the anemone to recognize the crab's tissues as safe. In this microscopic handshake, an agreement is signed, a truce sealed in molecules rather than gestures. From a behavioral perspective, the boxer crab's relationship with its anemones also redefines the concept of tool use in invertebrates. While chimpanzees use sticks to extract termites and sea otters wield stones to crack shells, the boxer crab employs living organisms as multifunctional tools, defensive shields, sensory devices, and respiratory aids. Tool use in animals is generally defined as the manipulation of an external object to achieve a goal. Here, the object is alive, self-maintaining, and even self-replicating. It is a biological prosthesis, a symbiotic upgrade rather than an accessory. This degree of innovation illustrates a level of behavioral plasticity rare among crustaceans, challenging long-held assumptions about the cognitive limits of marine invertebrates. Territorial disputes among boxer crabs further reveal how behavior and ecology intertwine. Individuals often establish small patches of sand or coral rubble, which they patrol and defend not through brute force, but through displays. When two rivals meet at a boundary, they engage in synchronized waving of their anemones, a duel of pattern and posture. The motions are highly stylized, slow, sweeping arcs followed by rapid jabs, each movement timed to currents that maximize visibility. Chemical signals released by the anemones may also contribute, as these displays occur most often when water movement is low enough for scent to linger. Such non-lethal resolution mechanisms are advantageous in dense habitats, where constant fighting could cripple populations. By turning confrontation into communication, the species preserves both energy and community stability. The crab's reproductive cycle adds yet another layer to the story. Female boxer crabs brood their eggs beneath the abdomen, guarding them with the same claws that hold the anemones. During this period, she continues to wield her living weapons, but modifies her behavior to prioritize oxygen flow to the developing embryos. The waving of the anemones doubles as a fanning motion, ventilating the brood pouch. When the larvae hatch, they drift away into the plankton, beginning their pelagic stage as tiny, transparent forms. Only after metamorphosis, when they settle back onto the reef, do they begin the search for their own anemones, repeating the ancient ritual of recruitment, grooming, and partnership. In the broader context of reef evolution, the boxer crab's alliance reflects a deep principle of marine adaptation. When survival demands innovation, life finds ways to merge. The boundaries between self and other, organism and tool, become fluid. Over millions of years, the selective pressures of predation and competition have rewarded such mergers, giving rise to coral-algae symbioses, fish-anemone partnerships, and now this peculiar crab that carries its allies like weapons. Each example represents a convergence of necessity and opportunity, proof that evolution favors those who can turn cooperation into technology. As the tide returns and the reef floods once more, the boxer crab resumes its rounds. The anemones sway in its grip, tentacles glowing faintly under the filtered sunlight. A curious goby hovers nearby, then retreats, deterred by the sight of those stinging pom-poms. The crab moves on, methodical and unhurried, its tiny world contained within a few square meters of sand and coral. Beneath the appearance of simplicity lies a system of astonishing sophistication, a living demonstration that even in miniature, evolution builds empires of strategy. The boxer crab's life is not one of passive coexistence, but of continual invention. Proof that intelligence in nature often wears the form of cooperation rather than conquest. Here, on the ocean floor, warfare and partnership are one and the same, an endless dance of borrowed power, performed beneath the gentle sway of the tide. Sunlight filters through the ocean in trembling shafts, splintering across the shallow reef like liquid glass. The water is clear, so clear that the world below seems suspended between light and gravity. Schools of chromis shimmer above the corals, their tiny movements bending the light into a restless dance. Then, from the blue distance, a shadow emerges, broad, fluid, and deliberate. A manta ray approaches, gliding as though it is a thought-given form. Its cephalic fins curl slightly forward, guiding the current toward its cavernous mouth. Around it, smaller fish scatter and regroup, giving way to this vast, gentle creature as it nears a coral outcrop alive with motion. The site is not a feeding ground or resting place. It is a clinic, an underwater marketplace of hygiene, negotiation, and invisible contracts. These are cleaning stations, places where large marine animals come to be serviced by smaller ones that specialize in removing parasites, dead skin, and debris. The relationship is ancient, reciprocal, and surprisingly organized. For the manta ray, maintaining a clean body is a matter of survival. Its wide, thin form, stretching up to 7 meters across in reef species, creates a vast surface area that attracts both microscopic and visible parasites. Tiny copepods latch onto the gill slits, feeding on mucus. Flatworms settle in the folds of the mouth and spiracles, and skin parasites graze on tissue. Left unchecked, they can weaken the animal, sap its energy, and slow its hydrodynamic efficiency. But here at the cleaning station, these problems are solved through cooperation. The manta glides in low, circles once, and pauses above the coral head, where cleaner wrasses and butterfly fish hover expectantly. The manta's arrival is not silent. Subtle cues signal its need. It loops in wide, slow spirals, the rhythm of its movements distinct from feeding or traveling behavior. This looping broadcast functions as a kind of advertisement, a message to the reef's cleaning specialists that a client has arrived. Cleaner wrasses respond quickly, darting upward from their perches to investigate. They assess the visitor with cautious proximity, confirming species identity and behavioral intent. Then, if the manta remains still, the work begins. The fish swarm over its surface like surgeons around a patient, each focusing on a specific region: the gills, the cephalic lobes, the underside of the wings. To remain stable in the water column, the manta adjusts its swimming delicately. A slow undulation of the pectoral fins counters the current, allowing it to hover in place. Its eyes, one on each side of the head, track the activity along its body. From a distance, the scene appears tranquil, but beneath the surface of this stillness lies a web of economics and negotiation. The cleaning station is not a random convenience. It operates as a market. Cleaner fish must balance multiple clients, each differing in parasite load, size, and risk. The manta ray, despite its gentle reputation, is still a predator in ecological terms, and cleaners must read its posture carefully to avoid accidental injury. In turn, the manta must wait its turn, adhering to priority hierarchies that emerge spontaneously from the behavior of the participants. Biologists studying these interactions have discovered that visit duration is influenced by 2 key factors: parasite load and current speed. Heavily infested mantas remain longer, sometimes for over 15 minutes, allowing cleaners to systematically move along their bodies. During periods of strong current, when holding position requires greater energy, visits shorten dramatically, behavior suggesting a calculated trade-off between cleaning benefit and energetic cost. Cleaners too adjust their behavior. When currents run high, they focus on high-value areas such as gill slits and the mouth, prioritizing zones with the highest parasite density. It is an unwritten agreement shaped by physics, biology, and time. Footage captured over hundreds of hours reveals even finer layers of organization. Mantas waiting their turn rarely intrude upon one another's cleaning sessions, instead circling slowly in the periphery of the station. These waiting loops create a kind of invisible queue, a flow of bodies coordinated without conflict. When a cleaning manta departs, the next in line glides forward, sometimes accompanied by a smaller juvenile that mimics the elder's movements, a possible instance of learning behavior. But not all mantas follow the rules. Occasionally, one breaks formation and swoops into the station out of turn, disrupting the rhythm. The response from the cleaners is immediate and clear. They scatter. The intruder is ignored. Deprived of service, the ray drifts away, its attempt at line cutting penalized by collective refusal. Over time, such behavior seems to diminish. The system self-corrects, relying not on dominance but on trust and reputation. From an ecological perspective, cleaning stations function as keystone nodes within reef networks. Their activity regulates parasite populations across multiple species, from turtles and reef sharks to parrotfish and moray eels. By concentrating cleaning interactions in specific locations, these stations create microhabitats of extraordinary biodiversity. The coral heads that anchor them are often among the healthiest in the reef, their surfaces kept clear of algae by the constant flow of visitors and nutrient exchange. The cleaner fish benefit directly from this arrangement, deriving up to 90% of their diet from the mucus and parasites they remove. For the reef, this partnership stabilizes an entire ecosystem. The physiological intimacy of cleaning is striking. Cleaner fish enter the manta's gill chambers, a space few other organisms ever reach. They move carefully among the filaments, plucking out parasites with surgical precision. Some even venture into the mouth, swimming past the massive rows of gill rakers that strain plankton during feeding. The manta remains utterly still, mouth open, trusting the tiny creatures that crawl across its sensitive membranes. Communication between them is entirely nonverbal. When a cleaner nips too aggressively, the manta flinches or flicks a fin, a warning to moderate its efforts. If the discomfort persists, the manta may leave abruptly, terminating the session. These gestures, repeated across countless interactions, shape a behavioral grammar that transcends species. Underwater microphones reveal another layer of this communication. The soft hum of water moving over the manta's body creates low-frequency vibrations that the cleaners may sense through their lateral lines. These mechanical cues likely help them synchronize movement, maintaining position even as the manta adjusts its angle to the current. The coordination is exquisite, a choreography of motion in which each participant reads the other through touch, flow, and pattern. On reefs around the Maldives and Indonesia, manta rays have been observed returning to the same cleaning stations year after year, sometimes at nearly identical times of day. This regularity hints at a cognitive map of the seascape, a memory not of landmarks, since reefs can change shape after storms, but of magnetic and current cues. Each station functions like a biological waypoint in the manta's migratory circuit, a predictable stopover in a life that spans hundreds of kilometers. These routes likely evolved under the dual pressures of parasite management and social exchange. Cleaning stations are more than service hubs, they are social arenas. Multiple mantas congregate here, forming loose aggregations that may serve as opportunities for courtship, hierarchy establishment, and information exchange. Within these aggregations, subtle behaviors emerge. Males trailing females often mimic their movements during cleaning sessions, maintaining proximity while displaying strength through endurance, staying motionless for longer, tolerating more cleaners, or holding position in difficult currents. Females appear selective, occasionally breaking off mid-cleaning to loop around prospective mates. The station then doubles as a social theatre where hygiene, health, and reproduction intertwine. Environmental changes threaten these delicate systems. Rising sea temperatures and coral degradation can disrupt the distribution of cleaner species, forcing mantas to travel farther between stations. Pollution adds another layer of complexity. Excess nutrients increase parasite loads, driving more frequent visits and lengthier queues, while sedimentation reduces visibility, hindering communication between clients and cleaners. The loss of a single active cleaning site can ripple outward, altering the balance of health across entire manta populations. Still, the resilience of this symbiosis endures. In one recorded sequence from a reef off Komodo, a storm surge had buried a long-established cleaning station in sand. For weeks, mantas circled the area in confusion, looping above the buried coral head. Then, within months, new cleaner wrasses colonized an adjacent coral rise, and the visits resumed. The market had moved, but the system reassembled itself, a testament to the adaptability of both participants. As the camera follows a single manta through its cleaning ritual, the details become hypnotic. The flick of its cephalic fins funnels water into its mouth, its spiraling movements suspend it weightlessly in the current. Dozens of cleaner fish trace lines across its back, their small bodies glowing electric blue against the grey velvet of its skin. When the final fish departs, the manta gives a single powerful stroke of its wings and ascends into open water, a shadow rising toward the sun. In its wake, the cleaning station settles into stillness once again, until another shape approaches, another client signaling need. In the silent logic of the reef, these transactions are constant and essential. Every act of cleaning is a negotiation of trust, every station a market of living health. Here, in the meeting of giant and minnow, evolution has written one of its most elegant equations, that survival at its highest form is not dominance, but cooperation measured in patience, precision, and shared persistence. The manta ray, in its sweeping grace, reminds us that even the ocean's largest wanderers rely on the smallest of its citizens to remain whole. The water here is shallow, clear, and alive with light. Morning sun pours through the surface like shifting glass, scattering over the undulating plains of seagrass that stretch across the lagoon floor. Each blade sways with the rhythm of the tide, brushing against its neighbors in a slow, endless whisper. For most of the reef's inhabitants, this is a place of refuge, nursery grounds for juvenile fish, shelter for crabs and mollusks, and grazing territory for countless invertebrates. But as the camera pans across the green meadow, a shadow glides into view, broad and deliberate, breaking the dappled light into ribbons. The shape resolves into a green sea turtle, ancient, deliberate, and utterly at ease in its world. With each stroke of its flippers, the creature moves like a thought carried by the current, neither hurried nor hesitant. When it descends, its shell casts a mottled shadow over the grass below, and the ecosystem responds. At first glance, the turtle's behavior seems simple. It lands on the seagrass bed, extends its long neck, and begins to feed, biting off blades in steady, methodical rhythm. But this act, repeated day after day across thousands of meadows around the world, is one of the quiet engines that sustain coastal ecosystems. The green sea turtle, named for the olive hue of its fat rather than its shell, is not just a grazer, it is a gardener. Its feeding does not destroy the grass, it renews it. The turtle's bite trims older blades before they accumulate too much detritus and epiphyte growth, algae, sediments, and microorganisms that coat surfaces and choke light. By pruning the grass, the turtle stimulates new growth, keeping the meadow in a perpetual state of youth. In this cyclical trimming, the turtle transforms from consumer to cultivator, maintaining the productivity of the very plants it feeds on. Each cropped patch of grass tells a story of renewal. When left untouched, seagrass blades age and decay, reducing photosynthetic efficiency. Their leaves grow tall but limp, trapping sediment and smothering younger shoots beneath. A meadow left ungrazed becomes stagnant, a dark, dense mat with little room for sunlight or water circulation. But where turtles graze, the opposite occurs. Shorter, denser patches sprout quickly after feeding, their roots growing stronger, their carbon uptake increasing. This regrowth fuels the base of the coastal food web, supporting small crustaceans, snails, and worms that live within the sediment. Those in turn attract fish fry and juvenile species, which use the trimmed meadows as feeding and hiding grounds. The turtle's appetite, measured in kilograms of seagrass per day, fuels an ecological chain reaction that extends far beyond its own diet. Beneath the turtle's slow, rhythmic grazing, the meadow pulses with activity. Small damselfish dart between the cropped stems, scavenging for disturbed invertebrates. Prawns and sea cucumbers emerge to sift through the loosened sediment, feeding on the organic matter exposed by the turtle's foraging. Even the turtle's waste contributes to the system. Rich in nitrogen and phosphorus, it fertilizes the seagrass, enhancing nutrient cycling. This is no minor contribution. Studies have shown that turtle-grazed seagrass beds can store significantly more carbon per unit area than ungrazed ones, locking atmospheric carbon dioxide into sediment for centuries. Through this daily routine of feeding and fertilizing, the green sea turtle becomes a keystone species in the global carbon economy, an unheralded engineer of both climate regulation and marine productivity. Yet the turtle is not the sole beneficiary of this equilibrium. Around it, a subtle alliance unfolds. Schools of reef fish, juvenile parrotfish, rabbitfish, and surgeonfish trail the turtle as it grazes, drawn by the disturbances it creates. Each bite sends tiny invertebrates and sediment plumes into the water column, which these fish snap up with practiced precision. The turtle benefits as well. The movement of the fish flushes out small crustaceans hidden within the grass, supplementing its mostly herbivorous diet with occasional bites of protein-rich prey. It is a quiet mutual partnership, no communication, no coordination, just shared advantage refined by millennia of coexistence. The choreography is striking. The turtle lowers its head to crop a patch. A pulse of sand rises and drifts down current. Within seconds, half a dozen fish move in, mouths fluttering as they pick through the cloud. When the turtle shifts position, the fish follow, forming a loose, flickering entourage that mirrors its every move. Each participant benefits in ways subtle but measurable. The fish gain access to disturbed prey, while the turtle expends less energy locating nutrient-rich patches where fish activity stirs buried detritus. In ecological terms, this interaction exemplifies a facilitative relationship, a network of behaviors that collectively enhances resource availability without requiring overt cooperation. Above this quiet exchange, the water carries the turtle's influence outward in invisible plumes. As it grazes, minute fragments of seagrass, rich with organic carbon, drift into the current. Some settle back into the meadow, fueling microbial communities that decompose and recycle nutrients. Others travel outward, carried by the tide toward the reef's edge. There, the nutrient-rich particles enter coral systems, sustaining algae and herbivorous fish populations that, in turn, support predators like groupers and reef sharks. The turtle's foraging, seemingly confined to a patch of grass, thus links entire ecosystems, from coastal shallows to coral strongholds kilometers away. The flow of nutrients it generates is measurable, forming what marine ecologists call a trophic bridge, connecting habitats that might otherwise function in isolation. Aerial footage of a lagoon during peak grazing season reveals these effects on a grand scale. The seagrass meadows, seen from above, appear as a mosaic of patterns, irregular pale patches where turtles have fed surrounded by darker, mature zones awaiting attention. Each cropped patch serves as both wound and heartbeat, proof of ecological renewal. In some regions, these patterns even help scientists track turtle populations, as consistent pruning leaves visible signatures across satellite imagery. The density and arrangement of these grazing patches reveal migration paths, population health, and seasonal feeding cycles. The turtle, unaware of its role as ecological indicator, continues its work, every bite a data point in a planetary experiment that began long before science existed to measure it. But this dynamic relationship is fragile. Over centuries, human exploitation, through hunting, egg collection, and coastal development, has sharply reduced global turtle populations. In many areas, the loss of grazing pressure has caused seagrass meadows to overgrow, suffocating under their own biomass. The irony is sobering. Without their grazers, these ecosystems designed for abundance begin to collapse under excess. Too much of a good thing becomes imbalance. The resurgence of turtles in protected zones has shown the reverse effect. Within a decade of population recovery in certain Pacific lagoons, seagrass productivity and species richness increased dramatically, along with fish nursery density. The simple return of one grazer recalibrated an entire web of life. Beneath the surface, the turtle's biology mirrors its ecological role, adapted for endurance, efficiency, and connection across habitats. Its lungs span almost the entire length of its body cavity, allowing rapid gas exchange and buoyancy control. A single breath can sustain it for hours of slow foraging, while its massive paddle-like flippers allow effortless travel between meadows separated by kilometers of open water. During migrations, green turtles navigate with uncanny precision, using magnetic field cues imprinted from their birth beaches. They move between nesting grounds and feeding sites that can be separated by entire ocean basins, yet many return to the same lagoons year after year. These migrations are not random wanderings, but deliberate circuits that transport nutrients across ecological boundaries, moving biomass from productive meadows to nesting beaches where females lay eggs that in turn fertilize terrestrial ecosystems through predation and decay. The interconnectedness of these processes underscores a larger truth. The green sea turtle is not a solitary animal, but a thread in an intricate web stretching from ocean floor to shoreline. Its life illustrates how energy and matter flow through systems that humans often divide for convenience: reef, seagrass, beach, as if they were separate entities. In nature, such boundaries are illusions. When a turtle grazes, it influences the coral reefs that protect the shore. When it nests, it nourishes the dunes that anchor the vegetation, preventing erosion. Every stage of its existence is a point of transfer between land and sea, life and decay, consumption and renewal. As the day lengthens, the turtle finishes its meal. The cropped patch around it is now brighter, cleaner, alive with motion. Tiny fish forage through the remnants, and the seagrass, its tips pruned and its roots aerated, prepares to grow again. With a few slow sweeps of its flippers, the turtle lifts off, rising toward the shallows where the light thickens and the water glows green with suspended life. Its shell catches the sun, flashing briefly before it disappears into the glare. In its wake, the meadow breathes again, recharging under the rhythm of tides. For an animal often seen as slow and solitary, the green sea turtle's influence is anything but passive. It reshapes its habitat through action and patience, cultivating meadows that feed worlds beyond its reach. Each bite becomes a gesture of ecological engineering, every movement a contribution to the ocean's continuity. From seagrass blades to coral reefs, from plankton clouds to migrating fish, the legacy of its labor drifts outward with every current. A reminder that in the architecture of life beneath the waves, even the quietest grazers sustain the world. The water off the Pacific coast is never still. It heaves and folds under the pull of tides, its surface a restless quilt of silver and green. Beneath that shifting mirror lies one of the planet's most complex and fragile ecosystems, the kelp forest. In these submarine cathedrals, giant strands of brown algae rise like trees, their fronds suspended by gas bladders that catch the sunlight filtering down from above. The effect is otherworldly. Shafts of light descend through the canopy, illuminating drifting particles and small fish that flit between the leaves. It is a realm of quiet movement and constant growth, a habitat built not from coral or rock, but from plant-like organisms whose survival depends on balance. That balance, though, is not maintained by the kelp alone. It is enforced, patrolled even, by a mammal whose size belies its ecological power, the sea otter. Floating at the surface, wrapped in a loop of kelp like a mooring line, a sea otter appears at first glance to be idle. Its fur glistens in the morning light, a dense, rippling armor of nearly 1 million hairs per square inch, the thickest of any animal on Earth. It rolls lazily, paws folded across its chest, sometimes clutching a stone, a clam, or a piece of shell. But below the calm facade, each otter is part of a living machine, one that shapes entire coastlines through its appetite. The story of the sea otter and the kelp forest is a story of reciprocity, a biological economy in which consumption becomes conservation. Left unchecked, sea urchins graze the base of kelp stalks, devouring holdfasts until the plants detach and drift away. In regions where otters were hunted to extinction, these urchin populations exploded, transforming lush underwater forests into wastelands known as urchin barrens. The result was ecological collapse. Fish populations plummeted, seabird colonies dwindled, and the coastlines themselves eroded without the kelp's stabilizing presence. But where otters returned, the system healed. Through nothing more than selective predation, they restored structure to an ecosystem that had lost its anchor. An adult sea otter consumes up to a quarter of its body weight in food each day, a metabolic demand born from life in cold water. Without a blubber layer like whales or seals, otters rely entirely on their fur and constant feeding to maintain body temperature. Their diet is diverse. Sea urchins, crabs, abalone, mussels and clams all fall within their reach. But their foraging is not random. Within kelp forests, different otter families, or matrilines, develop distinct tool traditions, learned methods passed down from mother to pup. Some lineages favor cracking abalone shells with selected stones. Others prefer hammering urchins against the seabed or using chest anvils made from flat rocks balanced on their bellies. These differences persist across generations, forming localized cultures within the population. This transmission of knowledge has ecological consequences. Certain otter families specialize in hunting along dense kelp edges, where prey is abundant, but access is challenging. By focusing their foraging near these thick canopies, they inadvertently protect the forest from collapse. The removal of urchins in these zones prevents overgrazing, while their discarded shells enrich the sediment with calcium carbonate, which benefits shell-forming invertebrates. The otter's preferences, in other words, create geographic mosaics of stability and renewal, patches where the kelp canopy thrives, providing both food and shelter to countless species. Each foraging event begins with a dive. The otter arches its back, tucks its paws, and slips beneath the surface in one fluid motion. It can remain submerged for several minutes, probing the seabed with sensitive whiskers and nimble forepaws. Using touch rather than sight, it locates prey hidden beneath rocks or within the kelp holdfasts. The dexterity of its paws rivals that of primates, each movement deliberate, each grip adaptive. When it surfaces, it brings its meal and chosen tool to the surface, rolling onto its back like a craftsman at his bench. The sound of stone meeting shell echoes faintly through the air, the percussion of survival. Pups, born wrapped in a soft, insulating baby fur, are introduced to this craft from the moment they can float. Mothers carry them on their bellies through the kelp beds, grooming constantly to maintain the microscopic air pockets that keep the fur waterproof. Each grooming session doubles as instruction. The pup watches as the mother selects stones, positions prey, and cracks open shells, learning the precise coordination required to feed efficiently. In time, the pup's own techniques will mirror those of its lineage, ensuring the persistence of its family's foraging style. Behavioral inheritance, rather than genetic adaptation, becomes the blueprint for survival. The kelp itself participates in this exchange. By anchoring their pups within its fronds while foraging, otters use the forest as a natural cradle. The floating canopy dampens waves and reduces exposure to predators such as orcas and sharks. In return, the otter's presence ensures that the kelp remains dense and unbroken, for the urchins that threaten it are kept in check. The relationship is not one of passive dependency, but of mutual reinforcement, a feedback loop where protection and predation coexist. The kelp gives safety, the otter gives stability. Scientific studies using aerial drones and underwater surveys have revealed just how tightly woven this relationship is. In regions where otters forage intensively, kelp forests grow thicker, with frond densities several times higher than in areas without otter activity. These denser canopies, in turn, buffer coastal ecosystems from wave energy, trapping carbon-rich detritus and providing nursery habitat for rockfish, sea stars, and crustaceans. The physical structure of the forest changes with the behavior of its guardian. Otters maintain not just the population of kelp, but its very architecture, trimming away the forces that would otherwise erode its foundation. Even the otter's discarded remains, uneaten fragments of prey, shells and bones, enrich the ecosystem. Their feeding stations accumulate dense piles of calcium carbonate, forming microhabitats for amphipods and small snails. This secondary productivity extends the otter's influence beyond its immediate diet. adding yet another layer of complexity to the kelp forest web. Ecologists refer to this as behavioral ecosystem engineering, where the actions of a single species alter the physical environment in ways that benefit many others. The return of otters to historical ranges has demonstrated this principle vividly. In Alaska's Aleutian Islands, where urchin barrens once dominated, kelp forests rebounded within a few years of otter recolonization. In California, the presence of otters has been linked to increased biodiversity and higher fish recruitment along rocky coastlines. Yet their resurgence also reveals the fragility of the system. Changes in predator pressure, disease outbreaks, or shifts in prey availability can quickly destabilize the balance. For instance, when sea otters decline, urchins proliferate and the kelp canopy thins, exposing coastal ecosystems to erosion and diminishing their capacity to store carbon. The otter's appetite, therefore, acts as a biological governor, its daily meals determining the fate of entire habitats. Within this dynamic equilibrium, human observation has introduced both understanding and irony. During the fur trade of the 18th and 19th centuries, sea otters were hunted to near extinction for their dense pelts. Their disappearance triggered one of the first documented cases of ecological cascade, the unchecked rise of urchins and the collapse of kelp forests. In essence, the removal of a single predator reshaped entire marine landscapes. Modern conservation efforts, grounded in that painful history, recognize the otter not merely as a species to protect, but as an ecological cornerstone, a living reminder that systems depend as much on behavior as on biology. Back in the present-day kelp forests, the otters continue their patrol. From above, their presence marks the surface with brief flashes of motion, a ripple, a roll, the glint of wet fur. Below, the forests they maintain sway in slow rhythm, their leaves filtering sunlight and converting it into life. Small fish weave between the fronds, crustaceans cling to the holdfasts, and urchins, though present, remain subdued, their numbers held in quiet equilibrium. The otter's actions ripple through every layer of this world, from the carbon stored in sediment to the balance of predators and prey that defines the reef. In the end, the sea otter's role in the kelp forest is more than ecological, it is architectural. Its foraging carves the boundaries of abundance and scarcity, shaping the environment through choices passed down by mothers to offspring. Each stone wielded, each urchin cracked, each pup groomed within the cradle of kelp reinforces a loop older than human memory, one where appetite preserves structure and behavior becomes the thread that binds ecosystems together. In these cold northern waters, where every heartbeat must fight the chill, survival is not about dominance, but stewardship. The sea otter, ever buoyant, ever hungry, ensures that the forest endures, a floating fortress built on the quiet rhythm of mouths, paws, and waves.